Good morning, dear participants. My name is Bohdan Derysh, and I'm representative as Ukrainian National University. Topic of my report is real-time military vehicle classification via CNN. Motivation for this research was, as we know, we live in time when Russia cruelly attacked Ukraine, and it's like the fourth year of this brutal war. So we need modern approaches to defeat this cruel and brutal enemy. So I use these 3 points that was main to start this research and write this report. First of all, modern defense requires rapid classification of military vehicles. Manual and classical machine learning methods lack speed and robustness. CNNs provide automated, scalable, image-based solutions. So, our research objectives was to develop a CNN-based system for real-time classification of military vehicles using RGB images under constrained conditions. To achieve this goal, we need to conduct research on the subject area and existing work on this topic. In summary, literature demonstrates a consistent shift toward deep learning-based architectures, practically CNNs and YOLO variants for vehicles detection and classification. These approaches deliver high accuracy, robust performance in variable environments, and real-time feasibility, making them highly applicable in intelligent transport, surveillance, and military domains. According to reviewed analogs, we would compare our solution and find main feature what make our approach best among others. So, for our dataset, we used open-sourced archive data, and other vehicles. It was 4 main classes like BM21, BTR80, T72, and T80. To recognize different type of these vehicles, we use like main features that represent them, like what type of moving base they use. It was wheels or trucks, what type of cannons, and dynamic defense they use, and other stuff that help us to recognize on image one particular vehicle from another. Image size was 128 to 128 pixel RGB format. Augmentation was flipping, rotation, and brightness. CNN architecture was used 3 conv2D layers, ReLU and max pooling, flatten, dense, and dropout, output dense with 4 classes, softmax, and it was near 12.6 million parameters. And detailed features of our CNN architecture demonstrate on table below on this slide. Training configuration. We train our machine learning architecture in this platform like Google Colab, because it's so practical and give all needed tools for programming, testing, and optimizing our approach. For optimization, we use Adam and loses space categories cross entropy for study with 10 epochs, and batch size was 32, and each epoch and their results we can see on the table below, and best result what we achieved was 67.47%, as we can see, and we talked about it in previous slide. Best training accuracy, test accuracy was 56.4%, validation accuracy nearly 36%, and loss decreased significantly. And correlation of our results we can see on the graphs below. And compared to modern solution and solution we overviewed in previous literature review, like related works, we have outperformed baseline ConvNet. ResNet remains superior in accuracy, and our proposed model, as we can see, results in the same parameters with two analogs, and our proposed solution is going pretty good compared to analogs, and according to this like first attempt, first prototype, and we can furthermore improve it, and it would be ready for use in real-time environment. I think this first attempt is pretty good, and like as I said before, we can improve in these categories like integrate transfer learning, expand dataset, reduce class imbalance, improve generalization with regularization and tuning, target edge deployment. And as a conclusion, convolutional neural networks are a powerful tool for real-time classification of military equipment. The proposed system achieves high accuracy and low latency, make it unsuitable for implementation in defense systems. The study confirms the feasibility of using CNN and military recognition tasks, and current limitation is training dataset, low validation accuracy, lack of full-scale testing in real-world conditions. So as it's only a prototype. Future directions is dataset expansion and class balancing, use of pre-trained models, regularization and combining overfitting, adaptation to edge devices and deployment on embedded systems, integration of additional sensor for multimodal analysis. Thank you for your attention. Happily wait to constructive criticism and your following questions.